大家好，欢迎大家百忙之中抽出时间来参加 Fluigent 2022年度首届双重乳化微滴网络研讨会。首先大家先等大概2、3分钟，其他可能会稍微晚一些到的其他的就是参会人员，稍等一下。再次向大家强调一下，我们这个网络研讨会的这个规模是严格控制的，所以这个交流起来相互交流是非常方便的。欢迎大家有任何疑问或者想法，在就是最后部分的就是问答环节，积极的与我们的液滴专家进行具体的沟通。欢迎大家提出问题或者想法，都不要有任何犹豫。如果想说英语的就说英语。如果想说中文的话，就说中文，没有任何问题。好，首先，我们现在就算正式开始了。首先我介绍一下今天网络研讨会的这个相关的主持人员。首先是Meziane，是 Fluigent 在科研类的产品经理，也是 Fluigent 里液滴方面的技术专家。他将主要负责第二部分，就是具体的那个具体的这个产品这个使用流程介绍以及原理。然后以及 Malik Soumare，他是 Fluigent 的技术支持工程师，他将主要负责今天的具体的实验操作，使用这个系统进行双重乳化实验的这一块的就是具体的操作。然后最后我自己是 Fluigent 的技术销售工程师，主要负责英国、爱尔兰、香港等地区的销售。今天来主要是作为一个翻译和那个一些基础的那个技术问题的解答。好，现在我们的 Adam 将进行具体的这个产品性能、原理与使用的一些就是理论上的介绍。Adam。
First, let's go back to the principle of the technology that we are using. So the technology that we are using is called the red drop. This is the device that we are using, as you can see here. It is based on the combination of a co-flow and a 3D flow focusing, emerge and in a confined metallic chamber. So the idea is that we are going to have a device which contains a chamber here, which will be filled with the continuous phase. And if we are zooming inside this chamber, you have two capillaries aligned together. One first injection capillary, which contain a double emulsion nozzle. So this is a nozzle inside the nozzle actually. And then this is aligned with an extraction capillary to collect the double emulsion. So how does it work? Basically we are going to, using fluid handling solution, we are going to inject flow of the core phase, shell phase, and the continuous phase. By regulating precisely the flow rate of the continuous phase inside the chamber and also the flow rate of the core phase and the shell phase, we will be able to generate double emulsion. How does it work? Actually, if you zoom inside here this junction, you can see that you have here a nozzle inside another nozzle. So the first nozzle is carrying the core phase and the external nozzle is carrying the shell phase. We are going to regulate the flow rate to inject the core phase and the shell phase. And then we are also regulating the flow rate of the continuous phase inside the chamber to allow to have squeezing in 3 dimensions, so all around the nozzle, to generate a droplet of the core phase and with also a droplet of the shell phase. That will allow to generate a double emulsion in the red drop. So the idea here is that the double emulsion is generated by the fluid handling solution, of course, but also is made by the geometry of the device, so the red drop device. This red drop has the advantage that you do not need any surface treatment or coating on the channel walls, because as you can see here, the continuous phase is always surrounding the double emulsion, and you never have any contact between the core phase and the shell phase with the channel walls. So you do not have any problem of wettability. One also advantage of the red drop is that it's a product which is really versatile and you can easily remove parts of the ray drop. For example, if you want to clean, you can remove the insert for the injection, where the injection capillary and the nozzle are mounted, and the same way the insert for the collection, where the extraction capillary is mounted. You can also remove some screws to open the chamber to clean it. If, for example, you want to remove your fluids and you want to go from water in water emulsion to oil in water in oil emulsion. This is something which is also possible. Another added value is also that as you can exchange everything, you can clean it really well, but also you can switch between different type of geometry. So for example, here we were presenting the double emulsion nozzle, but if you want to remove this one and make single emulsion, it is possible. You just need to buy another ray drop, not another ray drop, but just a simple nozzle insert that you will put the same way inside the ray drop. So you do not need to buy two ray drops for make single and double emulsion. You just need to change one nozzle to the other. And as you can see, this nozzle, this insert, is composing of a simple nozzle where you will inject the disperse phase, and you will be able, by regulating the disperse phase and the continuous phase flow rate, generate droplets. In terms of capabilities, with the ray drop, we are able to make different type of emulsion. This is the advantage also. Or water in water double emulsion, or you can make oil in water in oil emulsion, and you can also make partially miscible double emulsion. So in terms of water in oil in water, we have made water in desurf in water. Desurf is a surfactant from Fluigent, which is dissolved in fluorinated oil, so HFE 7500 here. And we have water, we have made also water in mineral oil in water, the same way with the same device. And as you do not need any coating, you can also make with the same device oil in water in oil double emulsion. So here we have tested mineral oil in water in mineral oil. And again, with the same device, you can also make water in solvent in water. So here we have used ethyl acetate. This is something which is really interesting when you want to make specific application for the, for example, the production of microcapsule made of biocompatible polymer, where the solvent evaporation is the polymerization process. So this is something we will see later in the presentation. In terms of also specification, here we were able to generate different type of double emulsion, and by playing precisely with the flow rates, with good stability and good precision, we are able to play with the shell thickness. As you can see here, the shell is a certain size, shell thickness. Then you have a shell thickness which is lower, so we have decreased the shell thickness, and again even much more lower here, so we have really thin shell here and a good stability. This is done mostly by the precision and stability of our fluid handling solution, and also with the performance of the ray drop. In terms of performance, we were able to generate at high frequency, around kilohertz, for the double emulsion production. We are able to generate from 80 up to 150 micrometer double emulsion size, but this is for the standard ray drop. However, we can also provide different type of nozzle. As you can see, it's geometry dependent. That means that if we remove the nozzle and put another nozzle which has different size, bigger size, let's say, with an extraction capillary bigger, you will be able to generate bigger double emulsion, and we can go up to 450, 500 micrometer double emulsions. Of course, it will depend on the fluid viscosity also, so it will depend on what you are going to use. And we can also decrease the size of the double emulsion, and we are able, with different geometry, to go down to 40 micrometer double emulsion. And in terms of monodispersity, we have highly monodispersed droplets, double emulsion, I mean, because the polydispersity was lower than 2%. Okay, now let's focus on some application, case studies that we did, and focus on microcapsule production. When we are talking about microcapsule, we are talking about aqueous core in a solid shell. And here, the first experiment that we did is using a UV resin shell. So the experiment was, for the double emulsion formation, was exactly the same. We were injecting polymer with a solvent here as a liquid phase in the shell phase, then an aqueous solution as the core phase, and a continuous phase which were an aqueous phase as well. We are generating the double emission the same way, as you can see on this small video. We are generating double emission with core solutions, the polymer shell surrounding, and in the continuous phase. Then after the generation, we have the collection inside the extraction capillary of the double emission, like this, which are generated. And the idea is to polymerize this double emission, which are at liquid state for the moment, under UV light. So we are using a UV light above of the tubing, the collection tubing. And under the exposure of the UV light, we will recover microcapsule. So double emission with an aqueous core and a solid resin shell here. Something which is important in this application is to have a good spacing between each double emission to make sure to have a good polymerization process and a good reproducibility. So for that, we have used the T-junction here with an external line of fluid handling solution. So we were generating continuous phase with pressure controller and the flow rate as well to increase the speed of the double emission when they are generated and to have a good spacing between each droplet. Basically, it's like having a co-flow here. So this is the first experiment for the, let's say, application with using a microcapsule and using a resin shell. Then we have used different type of shell because we have used an hydrogel shell which is called 𝗢𝗃𝗲𝗄. We have made oily core in a solid 𝗢𝗃𝗲 shell. So for this, the formation is the same way. The only difference is that as a core phase, we used soybean oil with a red dye to have better contrast. As a shell phase, we use 2% 𝗢𝗃𝗲 in water. As it is an hydrogel, it is dissolved in water. And as a continuous phase, octanol with span 80 as a surfactant to have a good stability. After the generation, we are collecting the double emission like this. And as you can see, you have nice and monodispersed double emission. When you have generated this double emission, you need to polymerize this double emission to have at the end a microcapsule with an hydrogel shell. For that, we use ex situ cross-linking. So we recover the double emission. We put this double emission inside a reaction bath containing a glutaraldehyde solution. And in contact with the glutaraldehyde solution, we were able to activate the cross-linking of the shell phase, so of the hydrogel. As you can see, 4 minutes after the double emission has been put inside the bath, you can see that you have a cross-linking which has started, and you see that you have a shrinking of the shell phase, so the shell thickness is smaller than after the connection. And then 1 hour after the cross-linking, you recover a microcapsule with a hydrogel shell, which is solid, and you have really a good shrinking and you have a thin shell. So this application is widely used for the encapsulation of lipophilic compounds or volatile products. Something that we have also measured is we have measured the leakage of the dye. So when, for example, you are working with drugs, you want to see if you will recover the good amount of drugs that you will inject in your core solution. So we have tested, and at the end, so 24 hours after the experiment, we have seen that the release of the dye was lower than 5%. That means that we almost have recovered and encapsulated almost the totality of the dye, so the drug if you are using it with drugs. And the drug release can be triggered using acid solution. Then we have used the same technology to make PLGA microcapsule. So PLGA is a biocompatible polymer. And the same way we have developed the double emission, we have produced the double emission the same way. So here the core is PBS solution, as you can see here. The shell phase is a PLGA dissolved in a solvent, and the continuous phase is a PBS as well. We have generated the double emission. Here the polymerization is in situ. That means that it's inside of the collection capillary. So the solvent in contact with the continuous phase will evaporate outside of it, and that will generate the polymerization of the double emulsion. So after the collection, we have that kind of double emulsion with a larger shell again. And then 15 seconds after the collection, you see that the shell thickness is decreasing. And 200 seconds after that, you can see that you have a thin shell, which is here solid. As you can see here, you have a microcapsule which contains an aqueous core. So it's something which is widely used when in pharma, when you want to encapsulate a drug inside PLGA microcapsule, because PLGA is a biocompatible polymer which is FDA approved, not something which is widely used. Okay, now it's time to focus on the experimental setup.
Thank you, Adam. So, as Adam says, we worked with Sequoia in association to make several packages in order to produce double and also single emulsion droplets. So this is the setup that we developed with Sequoia regarding the double emulsion package. So you can see on the left side of the slide the schematic that resume the setup itself. So Fluigent is specialized in the development of pressure controller. So those pressure controllers have a really high precision in the pressure that is applied, but also on the flow rate associated. So one of our biggest technology is the association of the pressure control with the flow rate sensor that we developed through an algorithm that will control the flow rate by increasing or decreasing the pressure accordingly to the flow rate that you want to achieve, and also the flow rate regarding the pressure that you applied. So you can easily work with both values during your experiment by applying pressure in your reservoir or by controlling your solution in flow rate, and of course control the pressure accordingly. So for this setup in particular, we choose to use 3 pressure controllers in order to control each phase. So 1 pressure controller for the continuous phase, 1 for the core phase, and 1 for the shell phase. So as you can see on the schematic, you will find 3 pressure controllers, 1 pressure controller with a big reservoir of 50 milliliters for the continuous phase. Just after this continuous phase, you will find the flow rate sensor that is directly connected to our flow rate, our pressure controller. As I say, to be able to control in pressure and in flow rate the solution. And just after this flow rate sensor, a panel of valve in order to use the rate drop the best way. I will get back to those valves just after that. So on both phase of core and shell, we choose to add 2 reservoirs of 15 milliliters for each in order to have the choice of the solution we apply on each phase. So for example, if you want to prime your solution and your experiment with a certain solvent in order to not waste a pressure reagent, you can start with 1 solution in the first reservoir, apply the pressure, be sure that the droplet have the size that you want to have, then turn the valve directly and use the other reservoir in order to use the reagent that is precious for you. So we develop those 2 reservoirs with the same pressure through a T-junction that will link the 2 reservoirs pneumatically, and just after that use the same microfluidic tubing in order to have the same hydrodynamic resistance and of course the same flow rate in both reservoirs. With this system, you will be sure that on both reservoirs and on using both solutions, you will have the same size and the same flow rate and also the same frequency of generation droplets. So if we go on the details of the content of the platform, you have this part that I just explained that will control the flow path, and the other side, which is here, using the optical device. In this optical device, you will find a camera, a light LED here, with a camera just behind it, and in the center of it, you will find a support where you will put your ray drop to appreciate the droplet generation. So maybe now we can switch to the production itself of droplets. So, as I said before, this panel will allow you to have a better priming of your solution inside of the ray drop. So, as I said, the pressure controller here will allow you to apply pressure in the reservoirs and get the solution goes directly to the ray drop. So first you will apply pressure or select the flow rate to select the flow rate of the solution of the continuous phase here in this line in order to apply pressure inside of your ray drop to make an environment of continuous phase to have this axis symmetric generation of droplets. So when I turn the valve to connect directly the reservoir to the ray drop, I will be able to direct the flow of the continuous phase directly to the ray drop. So whenever I reach the flow rate that is okay for me regarding the generation of droplets that I'm looking for, I will do the same thing for the shell phase. So for the shell phase, I will put the flow rate that is okay for me between the waste and the reservoir. Whenever the flow rate is stable, you can switch directly to connect the reservoir to the ray drop, like that, and do the single emulsion droplets. So as the continuous phase and the shell phase are different phases, you will have a single emulsion phases in the single emulsion droplet in the first time, in order to play on the size through the flow rate that you are applying to have really the droplet that you want to do. So whenever the size is okay for you, you will do the same thing for the core phase. So for the core phase, you will apply again the flow rate that is okay for you through the reservoir to the waste, and whenever the flow rate is okay, you turn again the valve to connect the reservoir to the ray drop, and then you will do double emulsion droplets. So to go deeper in this flow rate management, maybe Adam can show you through our software Oxygen the impact of the flow rate and the pressure directly on the size of the droplet.
Okay, now we are going to switch to another visualization where you can see also our software. So as you can see here, you have the pressure controller. So you can see that you have pressure controller for water, so the continuous phase, water with PVA here. The shell phase is mineral oil with a span, and for the core phase, this is aqueous solution. So the idea here is that we are going to play with the pressure to let's say modify the tune the size of the double emulsion. As the size of the double emulsion is quite nice now, I will stay with the continuous phase with the same flow rate, with the same pressure. So here I will having the same. I can either play in pressure or in flow rate. So for the continuous phase, it is really nice to stay in flow rate control mode, so you always have the same flow rate control. So for that, I just switch to this flow rate control mode. That means that the pressure will be adjusted automatically regarding the flow rate I'm asking. Here, for the shell phase, I have a good flow rate and good pressure here and good flow rate. I will just play with the core phase to show you how we can modify the shell thickness. So for example, here, if I want to have a larger shell, I will only decrease the core phase flow rate, and you will see that the core phase is decreasing and you will have larger shell. As you can see, we have smaller the core droplet inside the shell. And if I increase it, I can have thinner shell, and I can increase again and again to really have thin double emulsion with thin shell thickness. This is how you play, and you can play also with the continuous phase to decrease the size, and you can play also with the shell flow rate to decrease the size or to increase the size. It depends. Here, what you see is the order, and the measurements. So here, why I don't have any order is because Malik was playing manually with the flow rate, with the pressure controller. You can play with both local mode and live control. So I will switch to live mode to play with both pressure and measure. And flow rate, sorry. So that's all for the demonstration with the soft. And that's all for the demonstration. So if you still have some question, you can ask it now. We will answer. If you want to see some action from our part, for example, decrease the size, increase the shell, again, we can do it. Please feel free to ask. Before maybe we received a question, what we can do is, I wanted also to focus on one specific thing regarding the red drop. So as told you that the double emulsion are geometry dependent. That means that you can make double emulsion with standard red drop. If you want to increase the droplet size, you need to change the double emulsion, the standard, the double nozzle size or the outlet capillary. However, if you want to decrease below 80 micrometer, it is possible. For example, we have used, we were able to go down to 40 micrometer. And for that, we have used a different geometry. So instead of having a capillary aligned in front of a nozzle, we used another nozzle, a bigger one, which will allow to increase the shear stress locally at the junction. And this will allow to generate smaller double emulsions with higher frequency. So this is what we did, and this is something which is really interesting. We are still working on it. So this is something that it's available. However, we are working to again decrease even more to target 30 micrometer, for example, because we know that when you want to encapsulate cells in double emulsion for FAC sorting, for example, it's really important to have smaller double emulsions around 30, from 30 to 50 micrometer.
很好，支流的第一个问题，您好，我有3个问题，容器用极性容器怎么样？滤网会漏吗？极性容器，稍等一下。Adam?
Yes.
Une première question. Il demande si c'est possible d'utiliser les solvants polaires.
Solvant polaire?
Oui.
Actually, en fait, oui, non, tu vas traduire, pardon. Pour le solvant, ça dépend juste de la compatibilité. Comme en fait, le nozzle, il est fait en résine, en métacrylate résine. Donc, ça dépend de la compatibilité. Tous les solvants ne seront pas compatibles. Mais alors, pour la simple émulsion, on a des nozzles en verre qui sont compatibles avec tout, globalement. Et on va en avoir bientôt pour la double émulsion qui vont sortir. Donc, ah oui. J'ai une slide pour ça.
Tu as une slide à présenter, à expliquer?
Non.
OK, parfait. 刘主那个相当于是那个是的，我明白您意思。它这边相当于是那个兼容性。Adam, là après, je peux changer la version. C'est invisible un peu.
Ah oui, c'est pas clair.
刘指，oui, je peux juste changer. 抱歉，那个还没转 PPT， 它还没转过来那个模式，所以看着不是很清楚，有点糊。Adam 会把它调整过来。稍等一下。 可以，现在您可以看到这儿的话，相当于这个表格展示属于 Job 这个 chip 芯片里面，它那个相当于是一个喷嘴和收集管，所以你最关键的问题这儿相当于是它那个喷嘴和它的这个兼容性如何，这样的一些极端性的那个容器兼容性的情况，具体问题具体分析。其他的选择就是玻璃喷嘴，就是因为现在相当于是传统的或者说是经典的是树脂的 resin 的是树脂型喷嘴。目前玻璃喷嘴只在那个 Redrop 的那个 single emulsion， 就是单乳化那个芯片上有，但是很快会有双乳化，就是 double emulsion 双乳化的版本里也会有这种就是玻璃的喷嘴，就是它漏不漏的还是看你那兼容性。第二个问题 ，size 我看到是80到150微米，囊泡可以做得更小。具体的这个大小，我们 Fluigent 页面上有一个 droplet calculator， 就是液滴那个计算器，可以根据你所用的这个就是溶剂的这个就是 viscosity， 就是粘度，以及你施加的这个流速，相当于是最后实现的流速这个尺寸，以及产生的这个 frequency， 就是你的产生的这个频率。所以您问可不可以做得更小？具体情况要讨论，可以用我们网站上那个droplet calculator 做一个模拟。囊泡8到10微米。这个 size 的话，具体这个8到10微米，具体的8到10微米好像有点小。Adam, tu m'entends?
Yes.
Yes. Il demande finalement donc avoir une taille de entre 8 et 10 micromètres. Je crois, oui, pour double émulsion. C'est trop petit.
8 et 10, ça va être
Oui.
très compliqué. Attends,
Très compliqué.
Par contre, on est capable de descendre.
Okay.
Tu veux que je parle en anglais, peut-être?
Comme je veux. Je peux parler anglais ou français comme je veux. Sinon, je vais faire la traduction. Peu importe. Allez-y.
Okay, there is a question regarding the size we can go. Actually, with the double emission, we can go down to lower than 80 micron. This is done by not the same geometry. So for that, we put a counter nozzle in front of a nozzle for generating a droplet. So here, for example, we have this configuration, and with the double emission, we are able to go down to 42 micrometer. That will be difficult to go even below because the question was between 8-10, right, Jiakun? 10 micron, I would say that is really difficult to go down to that kind. However, going down to 30 up to 50 is something which is, I think, possible. We are working on it. We can go down to 40, that's for sure. And we are working in order to decrease down to 30, in order to be compatible with FAC sorting. So this is something that we are working on it, and we will have something really available really soon.
OK， 刘指，刚才阿达们说，好的，我看一下，好的，谢谢啊，不客气，不客气。大家有任何其他问题或者想法，或者欢迎就是继续咨询，欢迎大家提新的问题。泡沫是气泵还是什么泵？哦，这个可能您还从来没有用过我们 Fluigent 的产品，这个我就简单的说一下。我们这个呢叫 pressure controller， 就是刚才 Malik 几次提到叫 pressure controller， 其实呢我们可以叫它就是压力泵或者压强泵，大概的翻译是这样。它相当于是使用一个空气源，就是正常实验室里用那种就是气瓶什么的，使用一个空气源，然后这个 pressure controller 这个压强泵将会进行非常精密的控制，让这个压强非常的精密以及稳定，然后通过这个压强施加在您要使用的这个溶液试剂上，然后实现一个非常精确的，相当于是微流控，就是领域里一个精确的这个流量流速的一个控制相当于是实现这个。气泵的话，气泵相当于我感觉也可以这么说，反正需要一个空气源作为一个pressure source， 然后再接到我们的pressure controller， 就是这个压强泵上，然后进行一个精密的，相当于是流量的一个控制。在微流控领域，具体性的就是这个精度，就是精确性 accuracy， 以及这个就是 stability， 就是稳定性，对于最后微流控实验的这个结果的这个重要性是毋庸置疑的。越是精密，越是微小的这个领域，它相当于是更精密的仪器能实现更大或者最优化的一个实验目标的一个达成，是这样。 但是今天这个主要是整个 platform， 就是这个双乳化这个就是平台的一个就是展示，所以没有太多的涉及我们具体自家的这个 pressure controller 的一些就是具体的这个性能或者原理。如果感兴趣的话，可以就是跟我们那个大陆代理商微纳立方 microparticle 以前的北京燕京电子跟他们就是详细了解。如果就是想跟我们 Fluigent 这边直接联系，也可以跟我联系。没问题，就是可以就是稍微就是讲解一下具体的情况。那个相当于是我们的核心科技，就是 POM 这个本身是我们 Fluigent 自家的就是核心科技，我们的所有的专利和绝大部分产品都是来源于此。然后这个 Redrop 这个独特的芯片是来源于我们就是一个合作商，在那个比利时的 Sequoia， 他们相当于是做的 Redrop 这种就是全世界独一无二的三维环绕那个液滴切割技术，所以它在液滴方面有独到之处，全世界就那一家，我们是相当于是合作，就是双方两家的技术合作，实现了这个 Double Emulsion Platform 这个平台的一个相当于是建立使用，是这样。别新的留言，能留个联系方式吗？您是在大陆还是在香港？如果是香港的话，直接跟我联系；如果是大陆的话，可以跟我们大陆的代理那跟大陆代理商联，我把他们邮箱地址给您。如果感兴趣想跟我联系也可以。当然，我们大陆的生意基本上都是我们大陆代理商直接做。稍等一下啊，我把他的邮箱地址发给你。我把那个我都发给您了，您收到了吧？两个邮件地址。行。好，行，好。不客气，不客气。有问题欢迎跟我们大陆代理商或者跟我直接联系都可以。还有其他的问题或者好，不客气，不客气。还有其他的问题或者想法或者有要求，欢迎在那个 Q&A 里面就是给我们留言。如果大家目前就是没有其他的问题要问的话，我们还有那个 single emulsion 的那个 presentation， 就是单乳化的那个相当于 PPT， 可以给大家展示一下。如果大家目前没有其他的问题，就是想问的话，我们可以就是利用剩下的时间做那个单乳化的那个 presentation 的一个展示。如果可以的话，那 Malik 将开始，可以吗？大家，如果现在没有其他新的问题的话。好 ，OK。Malik, tu peux commencer la présentation de single emulsion pour l'audience, s'il te plaît.
Merci, Adam. À toi.
Okay, I will do actually the presentation. So we presented how we can make double emission, and however, I presented you also that using the red drop, you can just change the one insert, and you can make single emission. To do with it, so here, as you can see, we are in a configuration where we only have one nozzle and an extraction capillary, so connecting inserts here, a line. So we are able to generate simple emulsion. And what we did is we used this configuration to make PLGA microparticle. We have used lysozyme as it's a protein as an active ingredient to encapsulate. And so to generate the simple emission is the same way as the double emission. The only thing that is different is that you will have only one nozzle. So you are playing with the flow rate on the continuous phase precisely. You're injecting the droplet phase with the flow rate also that you control precisely. And then we will be able to generate simple emission. And when you're making simple emission, the same way as the PLGA microcapsule, here is let's say the level below, let's say, where you generate only droplets. You have encapsulation of lysozyme inside the droplets, which is composed of PLGA and solvent. And then at the outlet, you generate that kind of PLGA microparticle. Then you have solvent evaporation of the solvent that will decrease the size of the PLGA droplet. And with the same amount of PLGA, we have polymerization by evaporation. So we will recover solid microparticles where active ingredients are encapsulated, such as here lysozyme, but it could be also some drugs or mRNA, for example, and so on. In this case study, we have tested different concentration of PLGA, 0.5, 1, 2, 5, 10%, which is different because you will change the viscosity of the solution. So the result will be, the droplet size will be a bit different and the particle as well. We have tested concentration of 1% and 2% of lysozyme. We are able, as I said, to generate droplets from 50 micrometer up to 100 micrometer. So this is in the outlet capillary. However, so you have polymerization, solvent extraction during the transport of the droplet outside of the. We'll have a shrinking of the droplet, which in order to polymerize and generate microparticle. And the bits, the microparticle that we generated at the end were from 12 micron up to 30 micron. So this is the microparticle, not the droplet size. We were able to have highly monodisperse microparticle because we had a dispersion lower than 3%. And what's important is that we have tested and measured that the encapsulation was really high, the encapsulation efficiency, because it was higher than 95%. That means that the amount of lysozyme or active ingredient that you are injecting are almost totally recovered and encapsulated inside microparticle. Another case study that we did is for the encapsulation, for example, of cells inside alginate beads. We have made alginate beads, so the principle is the same. The only thing that is different is the continuous phase here, which will be fluorinated oil, and the droplet phase, which is alginate at 2% in water plus calcium EDTA. You're generating the droplet the same way, and then you are collecting in a collection bath, which is composed of fluorinated oil and acid acetic to generate the cross-linking of the particle. And you are going from droplet to alginate beads. For this experiment, we have tested 1 and 2% alginate, and particle size that we have generated were from 80 up to 140. And using this technique, you can control really well the generation of the inside the collection phase. That means that you produce really highly monodispersed droplets, and then they are generated and they are cross-linked. So you are generated microbeads, which are really highly monodispersed as well. Another application is a bit different. It's not droplet here, it's nanoparticle. So we can also produce nanoparticle with the red drop. So the idea here is to not making droplet, but having a co-flow where you will inject the lipid phase with an alcohol inside the continuous phase, which is PBS or aqueous solution. And you will have at the interface of the two solutions a diffusion and a mixing, which will generate nanoprecipitation at the interface. And you have a liposome self-assembly that will allow to generate liposome. The liposome that we are able to generate were from 20 up to 180 nanometer. And how do you play with this size? Actually, it's really easy. You just have to play with the flow rate ratio. That means the ratio between the lipid phase and the ratio with the continuous phase, which is aqueous solution. As you can see, we have played with the flow rate ratio from 50 up to 4 or 5 flow rate ratio. And you can see that the higher the flow rate ratio is, the smaller the nanoparticle size is. So this is how we worked, and we are able to generate highly monodispersed nanoparticle because the dispersion was below 10%. Why I presented you this slide is to show you that with the red drop, it's a really versatile tool that allows you to focus on one application, but you can also, by playing with the geometry and by adjusting some flow rate, you can also generate other type of emulsion, other type of microparticle, other type of nanoparticle, microbeads, hydrogel microbeads, and so on. So this is the idea. I just wanted to say also that we will have also another event if you are interested about double emission and what we presented today. We have a webinar tomorrow at 10 a.m. That will be more a talk of focus on one application, which is the polymerization of microfluidic produced liquid crystal double emission. And this is our customer Jan Lagawal, who is a professor at University of Luxembourg, who will be presenting. And he will present his work on cholesteric liquid crystal shell, how he used microfluidic-based, droplet-based microfluidic to make his emulsion, his double emission, and also present how he used the red drop platform to produce double emission and for his experiments. So if you are interested about the concrete application, that will be tomorrow at 10 a.m. and that will be an English session.
非常感谢大家今天热情参与我们的这个网络研讨会。那个如果没有其他问题的话，那今天就先到这儿。如果大家有兴趣的话，还可以参加明天早上阿达姆刚才说的10点那一场，就是跟那个卢森堡大学合作的那个另一场网络研讨会，但是那个会是全英语模式。如果感兴趣的话，欢迎大家参加。再次感谢大家今天百忙中抽出时间参与我们的网络研讨会。有任何其他的需要，欢迎直接联系我们的大陆代理商维纳立方 microparticle 或者直接联系我们 Fluigent 的公司。我们网站上都有联系方式。就这样，感谢大家，再见。
Okay, thank you everyone, and thank you for attending this workshop. We will send you the replay of this workshop session next week. We will also send you an email right after this workshop.
Une seconde, Adam. On a une question. Il demande le lien d'inscription sur le webinaire demain. 留纸稍微等一下，我这边弄。
We will send you right after this workshop session. We will send you a mail, which will give you the possibility to subscribe to the webinar for tomorrow. So we will send you in 1 hour or 2 hours, and you will also have the possibility to book a one-on-one meeting with one of our experts to discuss about your specific application if you want to have more details about the platform, if you want to have specific demonstration, or if you want to have specific information after the presentation.
所以就不用担心，我们会一块儿把那个就是预约的那个链接发在那个邮件里，不用担心，就是可以预约。而且就是如果除了那个还想1对1沟通的话，也欢迎跟我们联系，不用担心，可以吧？留纸。好的，好，行，好，那谢谢大家，再见。
Okay, thank you everyone. Have a good day.
Thank you, everyone.